Hi, hello. This is Arpana from Sri Venkateshwara College of Engineering of Electronics and Communication Engineering. So today I am going to explain you about the variation of wave function and the probability densities of a particle in a potential well of infinity wall height. First is introduction. The one-dimensional potential of a infinity is useful in order to demonstrate a model and also to understand the behavior of the particles in a confined systems. The wave function it will be describing the probability distribution of finding a particle in a particular state. The probability density it will be representing the likelihood of finding a particle at the specific positions. Basics of a wave function. Generally, the wave function is denoted as a xi, which is a mathematical function. It will be describing the quantum state of a particle. In the one-dimensional potential well of infinity, the wave function it will be satisfying this Schrodinger's equation. So this wave function is a complex value and also it can be represented as a combination of sine as well as the cosine functions. Basics of the potential well. The potential well is also a region where the potential energy will be constant. So in the case of the one dimensional, the potential well is infinite in depth and it will be also extending from the negative infinity to positive infinity along the x-axis or x direction. So whatever the particle is there, it will be confined within this potential well, so it cannot be escaped. Wave function in the potential wave. Generally, we know that the wave function is representing the state of the particle. Whatever the wave inside the well, the wave function is a combination of the two traveling waves. And outside the well, the wave function it decays exponentially. As we can observe this figure, infinite versus the finite potential wave functions. So in infinite, there is no decays exponentially of the wave function, but when we observe in the finite there is a wave function which is decaying exponentially. Then bound states and the energy levels. So when the bound states occur means when the particles of the wave function is confined within the potential well, then only the bound states will be occurs. Each bond state it will be corresponding to a specific energy level. So these energy levels are quantized and also determined by the dimensions of the potential well. Variation of the wave function. So when the energy level increases, even the number of modes in the wave function also increases. So generally these nodes are represents the regions where the probability density will be zero. Then the wave function oscillates more rapidly between the nodes as the energy level increases. And within the potential well only, the wave function will be changes as the particle moves. Whatever the amplitude and the phase of the wave function is there, it will be varying along the length of the well. And the variation also, it is depending on the energy level and also the shape of the potential well. Variation of probability density. So the probability density is the highest at the center of the well for the ground state. When we consider for the ground state, it will be highest and also at the center of the well. The probability density it will be spreads evenly when as the energy level increases. If the energy level decreases, there will be no even spreading of the density eventually. Even the probability density it will be becoming a more localized near the edges of the well for the higher energy levels. Relationship between the wave function and the probability density. The wave function it mainly provides the information about the amplitude as well as the phase of the particle's motion. The probability density also it will be giving information about the particle finding the particle at a specific position, and both the wave function as well as the probability densities are essential in order to understand the behavior of the particles that too in the one dimensional well of an infinite. Then variation of probability density based on the energy level. So Whatever the probability density we will be considered, it will be becoming more localized near the boundaries of the potential well. When it will be becoming localized means when the energy level increases. Then if there are higher energy levels or more, then the nodes in the wave function, it will be leading to the regions of a zero probability density within the well. The overall shape of the probability density, it mainly depends upon the specific energy level and also the corresponding wave function. So in order to become a valid wave function, there are some properties that is normalizable, continuous with its first and second derivatives, and lot but not least, limit extends to plus or minus x mod of z is equals to limit extends to plus or minus x mod of dou z by dou x, it should be equals to 0. Then superposition of the wave function. The wave function of the particle, it also can be a superposition of the multiple energy levels. Not only in one energy level, it can be superpositioned at many energy levels. And also these superpositions, it will be allows for a more complex probability density distributions within the potential well itself. Whatever the coefficients of the superposition is that they are helpful for the determination of the relative contributions of each energy level in order to overall the function. Then application examples means in which what way we will be using the examples in one-dimensional potential well. So the variation of the wave and the probability densities in the one-dimensional potential well is having applications in the various fields. So understanding these variations is a little bit crucial, but also in analyzing the electron behavior in solid state physics is also somewhat crucial. The principles explored in this model, it has been applied to the quantum computing and also the quantum mechanics research. So conclusion, in one-dimensional potential well of infinite, the wave and the probabilities of a particle, it will be vary with the energy level. As the energy levels are higher, there will be more oscillatory wave functions with the additional nodes. The probability densities, that means as the energy level increases, even the probability density also becomes more localized near the edges or near the boundaries. So this is the derivation of the one-dimensional potential well of infinity wall height for n is equals to 1 to 3 states. So now I am considering a one particle which is having a mass m inside a potential well, and it is also having a width a which is moving along the x direction. So and also whatever the potential is there inside the well, we will be considering it as a 0, and outside the potential is infinity. So according to based on this Quadratus wave equation, we will be deriving this equation. So here the main equation we got is E is equals to n square h square by 8 ma square. So at the n is equals to 1, that means it is representing the ground state, and whatever the corresponding energy is there, it is called as a ground state energy or 0 point energy. So for ground state energy, when we substitute n is equals to 1 in the equation, we will be getting E naught is equals to h square by 8 ma square, and n is equals to 2. It is representing that first excited state, and the first excited state energy is represented as a E1. So when we substitute in the equation, we will be getting E1 is equals to 4h square 8 ma square, which is equals to 4 E naught. Then n is equals to 3, which is representing the second excited state, and also the energy is called, corresponding energy is called as a second excited state energy, where we will be representing as a E2. E2 is equals to 9h square 8 ma square, which is also equals to 9 E naught. So thank you for giving such an opportunity in order to explain this topic. Once again, thank you.